All right, good afternoon, everybody. So what we're going to do today is we are going to do the last problem for problem 4, which will be the final TREAP problem. And then what we're going to do is we are going to learn about a new data structure and its improvement upon ways that we can do priority queues, and we're going to call it a binomial heap. It's going to be very representative of the type of data structure that you'll be using to solve problems when you get later on into the algorithms course. So the first thing I'd like you to do is I'd like you to finish up these instructions to do lecture 25, and then go back to your lecture 24 folder. We're going to finish up that problem 4. The other thing we're going to do today is we're going to go over some sample problems and examples of how of specific C++ standard template libraries, standard map, standard set, standard multi-set that use red-black trees, because there will be 2 problems like that on your final exam. While you're doing that, I want to point out a couple quick things. Please send an email tonight. It's listed on the course page. I have a link about how to do this. Send it out tonight to your industry mentor to schedule your presentation for next week. The rules are, first CC me and your project manager. Your project manager must be available for your entire presentation, because they're going to be the one who can be there for the entire time, will be able to grade your work. I am going to hop in to all the presentations, but I'm going to, in the event that 2 are scheduled at the exact same time, I will take the first 15 minutes for one group and the second 15 minutes from another group, and so on. So please make sure you get that sent today. I also have a plan for what happens if we don't get an initial response. So we email today, then if we don't hear anything back, we'll try Thursday. If we don't hear anything back on Thursday, then I step in and email on Friday. So that way we can get all the pre-turnship presentations scheduled. All right, so please go into lecture 24, and I'm going to come over here on the left, and we're going to work through, so it's going to be your left, my right. And what we're going to do is we are going to work through this together. I'm going to push it down. Okay, good. I'm going to walk over here. All right, so the way that these problems are always set up is for a tree, it's a combination of a tree and a heap. You've got the sorted elements and then the probability of the value that we're going to use. And that's how we're going to be heapifying values up. So for this problem, we are initially going to insert D10. And so the steps are, we'll have D10 here, and then we insert E47. So initially, I put in E47 like this. So what should I do next? What's the next step I should take in order to get this tree up? Yes. You had your hand up. Yes. Absolutely right. We got to rotate this because 47 is bigger than 10. So this way, E47 comes up here and D10 comes down here. We perform that rotation. We have the same ordering, so the binary search is preserved, but now we have the probability higher in the tree because 47 is 4.7 times more likely to be accessed than D. So we want that higher in the tree. Next, we're going to insert F18. So F18 in order is put here, and we see that 18 is less than 47, so we leave it alone. Next, we're going to insert A37. So A will initially be inserted as D's left child. So here's a good rule. It's less than 47, but it's greater than 10. So what we're going to want to do is we're going to heapify it. So A is going to come here, and D is going to come down here. So we have A is 37, D was 10. And so now we have maintained again the ordering, but now we have the heapified property. Now we're going to insert C92. So C92 is going to be all the way down here, like so. So we start there, and then the process is we look locally. So initially, we're going to make D the right child of C. So it initially looked like this. We'd have C92 and D10, like so. But now we have A37 here. So now what we're going to do is we're going to do this rotation, right? Because we have this ordering. We know that C is greater than A but less than D, and we have the heapification. So this becomes A37, D10, and C92. Does everybody see that? So the next level is, what do we do here? Because at this point, we have E47 is above there. So what do you propose we do in this case? What should we do here? Who wants to take a stab at this? We're trying to get C92 to the top. Let me check the Slack as well. Yes. Very good. So that's exactly what we would do. We would bring C92 up to the top. So you have C92. E47 was up here. And as you correctly pointed out, D10 is now going to be the right child. And E's original right child was F18. So now we have A37 over here. So now we're going to insert B7 and G35. B7 simply goes here. G35, G initially would come down here. We'd rotate this up. So then this becomes G35, and we have F18 down here. So does everybody understand how I got to this point? All right, so then the next thing you'll see on one of these type of problems is a delete. And here we have C92. So just to refresh your memory, what's going to happen is we're going to apply heapification. So we get rid of C92, and initially we're going to bring the largest value on the left-hand side up, just like we've done in every other deletion, but now we need to move it down. So we have to maintain the ordering. So we know that E is bigger than B, and we take a look at A. 37 is higher than 7, so we want to move this up. Actually, hold on. A is 37, B is 7. So we're going to pick 47 because 47 is going to be higher. So if I switch this out, what's the problem if I bring A37 up here? If I do this, what's the big issue with this heap now? Who wants to tell me what's wrong with this? Why is this a wrong answer? Yes. Absolutely right. We now have a value 37 that's bigger than 47. So we have violated our property. So what we will do instead is just like we did with heaps, we check which one's larger, in this case 47, and we're going to move this up here. So it's going to become E47, and then we put B7 here. Then we have to maintain the, wait. Hold on, I'm sorry, one more. Because we do this, we have to do rotation. And then this would become E47 up here, B7, D10, A37. Now we got it. So now I would want to do this rotation since 37 is bigger than 10. So now it becomes A37 up here. This will eventually, just in the interest of time, and F18. And I believe this was choice A. I forget exactly which one. But we see that we perform those rotations because we have to maintain both the ordering and the size. Right? So we see how, in the end, we have our heapification property, but we also have our sorted property. Right, does anybody have any questions about this? I'm going to go up real quick and check the Slack to make sure that those of you who are in your dorm or elsewhere in the world have the opportunity to ask a question. Okay, why did B move up upon C's deletion? Same thing, we initially want to move the left value on the value there. Okay, does anybody have any other questions? Okay, so G was initially over here at G35. So I probably, when I was transcribing here, so G35 was, I realize it's not showing it, but G35 was up here. So eventually this would become G35 would be on the right-hand side and F18 would be below that. All right, so what I would like you to do next is I would like you, okay, so it's D, not A, my apologies. So what we want to do is go down into lecture 25. And what we're going to cover today first, we're going to be covering standard template libraries that use red-black trees. And what I want you to do is show you an example of these different code segments and how you would walk through and try to see how it is that they're working and why it is that we understand what's going on underneath the hood. So in this case, I have 3 standard template libraries that are based upon red-black trees. The simplest one is standard set. Standard set is simply a conventional red-black tree. If you actually look inside and look at the commenting inside of standard set, which is available and you can actually do on the Notre Dame machines, and we've done that before with stacks and queues to see that the underlying data structures were singly linked lists and doubly linked lists. In all of these, the major data structure that's being used is a red-black tree because it provides a good balance for a anticipated uniform distribution of elements. So we've learned about probabilistic trees where we don't have a uniform access. We've learned about splate trees where we might want to take advantage of some kind of locality. But in a generalized case where we don't want to have excessive switching, but we want to maintain that binary search, we want to have that relaxed balance, which is why the designers of these data structures selected the red-black trees. The difference between standard set and standard multi-set is that multi-set is a red-black tree that permits duplicates. So standard set, no duplicates permitted. Multi-set permits duplicates. And then we have a standard map. So you all might be familiar with this, with maps that you've learned in, for those of you who are taking systems programming this semester. And you're familiar with maps. And in here we talked about unordered maps. And an unordered map is basically using the hash function to get to a specific location. The input into the hash function is the key, and then the value becomes what we store in that location in the underlying dynamic array. In a standard map, we have key value pairs. The difference is, with the key value pair, that the red-black tree will sort the elements by the key. And then the value is what's stored inside that node. So if I had a pair, let's say I had 3, 6, 2, 5, 1, 7, right? The way that the red-black tree, we put in 3, then we put in 2, then we put in 1, and then it would perform this rotation, 2, 1, and 3. Then this becomes black, like so. So it sorts by the key, not the value. If I look up the value, if I go dot second here at 2, it'll give me the value 5. Right, so what I want to show you first is some code in this set test. So in the code that you downloaded, you go into source, you'll see that I have several files here, and one of them is called settest.cpp. So I'm going to do vim settest. My backspace isn't working today. And so what we have here is a set of insertions into a standard set. And what's going to happen is, when I insert these values, I have 40, 30, then I print the tree. I'm going to describe this particular code in a moment. And then I'm going to call erase on these. So what's going on is when I insert them, it'll sort them using the underlying red-black tree. And then if I iterate through, it's going to print out the values in order. So if I go into lecture 25 and I go into set test and I zoom in, here's what's going on with print order. So I have this. I could even improve the code by doing const and call by reference. And then I use this smart iterator, which iterates through the entire range. And I call it on print tree. And so, first of all, somebody remind me what's actually going on here in this iterator. What is this doing? Yes. Correct. So it's iterating completely through. And so in main, I'm going to show you the values that I insert first. I'm going to put in 40, 30, 60, and 20. So these are the values that were inserted. When I do this code, what do you think is going to print out? What do we suspect when I have those specific 4 values? Anybody want to give it a try? If I'm iterating through this and I've inserted these into a red-black tree, what order is it going to print out those 4 values in? Anybody on the Slack? Anybody? If I'm trying to print out a red-black tree, what do you think I'm going to print out here? Someone take a guess. Anybody? All right, so Kristen says 20, 30, 40, and 60, and she is correct. It's printing in the correct order. It's just printing in 20 in the order, and it's sorted because that's what red-black trees do. 20, 30, 40, and 60. So if I go back here, and I go make set test, what's going to happen, first I need to go up 1 level. It's going to go through this whole process and print out the elements in the specific order. So first it's going to say 40 and 30, and then I call print in order tree, and it prints out 30 and 40. Does everybody see that? And then I insert 60 and 20, and it gives me 20, 30, 40, and 60. And then I'm going to call erase 40. Erase 40 is going to call the deletion on the red-black tree. And so it's going to print 20, 30, and 60. And then I try to insert 40, 50, 50, and 10. So at this point, I have 40, 30, 60, 20. I have erased 40. Then I insert 40 again. I do 50. We try to insert 50. And then I insert 10. So does somebody want to tell me what the order will be when I print this out after all those insertions? All right, I want you all to be more active, please, all right? You're going to see a problem. I promise you, you're going to see a problem like this on the exam. You're going to want to have tried to practice this. So please, what's the order? What do we expect here? Yes. 10, 20, 30, 40, 50, and 60, right? So the crucial thing is, is it going to print 50 twice? Yes or no? Okay, a lot of heads shaking no. So I see that so a standard set does not permit duplicates. And if we take a look at what printed out when I ran it, we'll see here, in this particular line, it does not print a second 50. And so I go through the whole process of inserting all these other elements. Now, if I do multi-set and I do the exact same thing, that's where we're going to get the duplicates of 50. So if I run make multi-set, we're going to see that in this case, it's the exact same code, but you see that line that I've highlighted, that it prints out a duplicate. Does everybody see that? So multi-set permits duplicates and will print them in sorted order. Set does not permit duplicates. All right, does anybody have any questions on that? So I have another question. I want to go here. So remember before, I pressed save, and I'm just going to update this real quick, even though I didn't really do much to it. I've run make set test, and it compiles and it runs everything, right? If I run make clean, and now I'm going to do something here. We see here that it says const. If I delete this, what do we think is going to happen? So let me delete that and update it. I'm going to type in clear and then make set test. What do we think is going to happen here? Anybody have a hypothesis on what will happen when I press enter? Yes. Correct. So the theory is that it's going to give us some sort of error regarding constness. Did I run the same correct file here? Oh, my backspace is not. There we go. I'm taking this out. Set test. Should not have compiled. Okay, that's unexpected. All right, so see if I can actually produce this error. Am I actually looking in the right folder? I hope I am. I am not, that's why. My apologies. So if I go here, and I get rid of this const, and now we're going to see what's going to happen here. And we see we get this error. And now I'm going to read through it, And it says invalid initialization of reference to type int ampersand from expression const int. So we see here that in this I have, with the template, it overrides and gets the value from here. So the question is, why is that bad? Why does somebody have a theory as to why this is not good? Why would the computer tell me we can't run this? What's going on here? Anybody have any guesses? I see that there is somebody typing something in the Slack. How's everybody doing? Like, even this is a little less interaction than I normally get from you all. Are you all okay? You're not even responding to that. Okay. But seriously, like I promise you, like, you're going to want to practice this. This is important. Your potential for going out of bounds when you try to build a tree. So this is a good guess. When you call by reference here, this goes to the location. And if I were to try this, if I were to say cur equals 5, if this was a linked list, that would be valid code. I would actually be changing the data inside the linked list. Why, in this case, for a red-black tree, would this be bad? Why would it be bad to change? Yes. Absolutely right. There we go. So what's going on here is, let's say I'm just going to put up I do 10, 7, 5, 3, 12, 11, and 13. Right? So we have a random tree here, and I'm iterating through. And so when it's const, it'll print out 3, 5, and 7, 5, 7, 10, 11, 12, and 13. If I try to change this at one point, if I try to change this to 5, then that will correspond to this. Does everybody see that? So what's going to happen is, if we don't keep that as const, you're allowing somebody to change the value inside the node without actually maintaining and balancing the tree. So that is why when I do this, it's going to insist that I keep things const. So I'm going to run make set test again. We see that we've updated it, and now it works perfectly. Does everybody see that? So this is an important thing. If you are using C++, you should be able to understand that. I should be able to ask you a multiple choice question on the exam, giving you a code segment that says, this is going to produce a compiler error. Why is that? And you should be able to select the reason why. Hint, hint, wink, wink, nudge, nudge. All right, so if I am reversing orders here, so let me go up to here. What I'm doing in this code, let me try to make prop 1. Is this it? Okay, that's not quite it. I'm going to show you some code here, and then what I want you to do is we're going to compare set and multi-set. So here, what's going on is I'm inserting several values, and I've created a red-black tree and a stack. Does everybody see that? So what's going to happen is I insert all the values, and then I call this function. Inside this function, I'm iterate through the red-black tree, and I push all the values into a stack, and then I pop all the elements off. So what I'm going to do is I'm going to put up 5 random values. I'll do 10, 17, 9, 6, and 34. At the end here, when I iterate through, when I remove an element from the stack, I print and then remove, what will be the outcome given these values? And so Connor, I see that you typed the correct answer to my previous question in the Slack. What's going to be the order here? Yes. 34, 17, 10, 9, and 6. That is absolutely right. So the reason why is because the standard set sorts the values, and then the stack reverses them. What happens if I did this? If I did 10 and 34 here? If this was a set, what's the output going to be? Is it going to be any different? No, a bunch of people shaking their heads. No, that's absolutely correct. What's going to be the output if I say this is a multi-set? So those of you in the Slack have pointed this out. So somebody tell me, I see a couple people typing things up in the Slack. What's going to be the output here when if I change this to multi-sets? What's the first number that's going to print out? I see somebody's correctly, Sebastian correctly said there would be duplicates. So someone tell me the first value. 34. What's the next value going to be? 34. What's the next value going to be? Very good. What's the next value going to be? What's the next value going to be? This is important. 10. Very good. Then 9, and then 6. If this was a multi-set, it's duplicate. If it's just a set, it's single. Okay, and so this example here gives the difference in the outputs if we're reversing it. Standard map, what I've done here is you sort by key, and then I have a const standard pair, and it's going to print out first and second. What you're going to see is I have 0, 1, 2, I'm just doing this in the interest of time, 0 through 6, and you do this, they'll say, wake up the echoes, cheering her name. It's not going to sort by the string order. It's going to sort by the key. So if I print something out like that, that's the way it's going to work. All right, so what I want to do next is I want to go through an interview type question, and we're going to see how we might solve this. So the interview type question is, we are given a set of numbers. And in this set, every number has a duplicate but one of them. How do we find which number that is? And so we don't know how big it is, and we don't know, there's only one value that is not duplicate. When are the values printed in ascending order versus descending order as just presented? So this is an important thing. I put it in a stack, so it reverses it. You have to know the underlying data structure. So it's in descending order if I put everything into a stack and then pop them all off the stack. It will always be by itself in ascending order. Okay. Let me know if that addressed your question. All right, awesome. Okay, so here is some steps we might take. We might say first crack is a hash table. Good thing is we have lookup time, right? Big O1 lookup time, so that's really good. We get through all the elements. But the issue is, this doesn't necessarily tell us if that's not the duplicate. So in a worst case scenario, we would have a situation where the last value that's inserted is the non-duplicate. So we would hash it. We'd say, well, it's not there. That's good. We know we haven't found it yet. But then we would never come around and check to see whether or not it was actually a duplicate. So this is when people go through interviews and try this particular type of question, that's where they get hung up. It's like, okay, I'm going to hash and I try everything, and that's big O1, and that's really good, but I can't prove it in certain cases. So the way that you would want to attack this problem is to say, all right, actually I said through all that, what if we used a standard set? What if we said, all right, I'm going to go through and I am going to make a small trade-off in search time from big O of 1 to big O log n, but I know that when I'm done with this, I can have a guaranteed way of determining what that duplicate, what that non-duplicate is. And so here is how I can prove this. I'm going to use two methods, count and erase. So this is in standard C++ 11, not C#, C++ 11. And after in C++ 14 and C++ 20, all of these methods, just like standard unordered map before, will now have a new method called contains, which will check to see if that's values in the hash, or in this case, in the red-black tree. But here, we're going to use the method count. And so what I'm going to say is, if it's not there, I'm going to insert. And then I'm going to say, well, if it is in there, I'm going to erase it. And then I'm not going to insert the other one. And so what's going to happen is, when I come in, when I get that second value, I will try to, let's say 10's already in my red-black tree, and I've come across the second one. I will erase 10, rebalance the tree, and don't insert 10, so now neither pair is remaining in the red-black tree. As a result, what's going to happen is, if we follow that process all the way through, there will only be one element remaining in the red-black tree when we're done, and that element will be the non-duplicate. So then all we have to do is just print the first element, and that will be our result. So let me walk you through an example of this. So we have 10, 2, 8, 8, 5, 3, 2, 3, and 10. So in this case, 5 is the non-duplicate. And so plus I'm going to do this, plus this is an opportunity to go through a small review of red-black trees too. So you're going to see it in the animation, get some insert and delete practice. So the first thing we're going to say is, all right, 10's in the tree, 10 is the root, 10 is black. So now 2 is going to be the left child of 10. And that's just inserted as red. Next, I'm going to insert 8. 8 will initially be the right child of 2. And now we have a red parent and technically a black uncle, because 10's right child is null. So this will allow us to initially do that case. So the first case is we rotate, we move 8 down, like so. And then we move to case 3, which is now 8 will rotate up. Then we will recolor 10 and 8. Okay. So now we have the insertion here. And then the next part is, well, now I'm going to try to insert 8 again. But the first I check to see if it's there. 8 is in there. And so now I'm going to try to delete 8. So I delete 8. We would move 2 up, like so. And then we're able to leave this tree alone. So now I want to insert 5. 5 is initially going to become a red child, specifically the left child of 10. And then I'm going to perform the case where I rotate 5 and 10. And then I can rotate left and get 5 will be the new root, and then we'll recolor 5 and 2, like so. Then I'm going to insert 3. 3 is going to become the right child of 2. And we see that we have a red parent and a red uncle, black grandparent. We recolor all of them. We get to the top and we recolor the root, which will become 5. Next, I try 2. 2 is already in there, so we're going to move 3 up. We're going to see that 3 becomes the new left child of 5 in his black node now. Then I check 3. We're going to delete 3. We see that I lose the value on the left, which means I'm going to have to recolor 10. And then the last element is 10. I see that 10 is in the tree, so I delete it. And now the only value left is 5. So the crucial thing is, with a small trade-off in time, I now can guarantee that I can find the element. Does that make sense? Awesome. Right, and so here's the code I wrote to do this. And in the function, I have a standard set, and I bring in a vector of elements. And then what I do is I iterate through the vector, and then I say, well, if it's not in there, meaning that count is equal to 0, then I insert it into the red-black tree. If it is in there, then I call erase. Then what I have here is I iterate through the red-black tree and print it out in order. Now here's the interesting thing. Because it's at the top, it's only going to grab the first element, and so we'll print out 5. And the question is, would this be big O log of n? Yes, that is absolutely right. This is big O log of n, but we can't use the hash table. And let me draw up an example of what I'm talking about. So let's say I have the same thing. I got 10, 8, 3, 8, 3, 10, and 4, right? So with the hash, I would hash 10. I have an int there. I find 8. That's the first element. I hash 3. One's element's there. I hash 8. I would say that's 2. And I do 10. And then I hash 4, and I know there's 1 element. But now, when I get to the end and I have my data structured like this, in order to figure out which one it is, I'd have to iterate through every single bucket to find the value that's 1. And we can't just keep track of it because there's going to be a point in which there's several elements that only have 1 element in there. So in order to make up for it, we do a very small trade-off in time to big O log of n. And then, but this allows us to guarantee that we know the solution at the end. Right, let me know if that addressed your question. Okay, so final exam expectations. There will be 2 interpret code type questions. One will involve either set or multi-set, and the other one will involve standard map. And what we're going to do for the next 2 example problems is we are going to work through these together. I'm going to show you the good way to go about it, what you need to remember as you're going through this type of problem, and then the difference between set and multi-set. The other thing is I have a couple of example questions. It's very similar. If you look at lecture 18, it'll be similar to a problem that I did earlier this semester. And the whole idea is that you'll look at this and say, based on this, I expect that this particular binary search tree node would do this task. And so that's available. So these will be the type of questions. And I will be releasing on Thursday after the lecture, I will be releasing the sample exam. And on the sample exam, I'm going to have the breakdown of how much time I expect a student to do on this assignment. So let's work through these 2 interpret code problems together. The first thing that I want you to do is in your lecture 25, I want you to run make prob 1. And when you do that, you're going to see that it gives the entire code segment and then a set of potential solutions. So when you get to this type of problem, the first thing I want you to do is go to main. Don't worry about the functions. Don't worry about everything else. Get that all out of your head. Go to main first. Think just like the computer. And in this case, we see that in problem 1, I have a map. So a standard map, think to yourself, oh, standard map, key value pair, sorts by the keys, red, black tree. So right off the bat, before you even start the problem, you can tell that there's going to be some sort of sorting going on in the solution. So I might have some sort of order where one of the choices is it's put in the order that I inserted. That's obviously wrong. So right off the bat, we know sorting, key value pairs, I got to pay attention to what's going on there. So then I have 2 functions. Just break it down to func, and we're going to start out with 6. So now what you want to do is go up to this function and see what it is that we're trying to do here. So I've initially passed 6. And so here I have if val is greater than 1, func the map val minus 1. So what am I also testing here? Recursion, outstanding. So I see that, well, val is 6. Now I'm going to do 5. So greater than 1, 4, 3, 2. And then when I get to value is equal to 1, so when val is equal to 2, I'll pass it. When val is equal to 1, it skips past that and now moves into the if statements. So in the if statements, when you're doing recursion, you're going to move back up. In this case, we have an if statement. It's if val mod 3 is equal to 0. In this case, it's 1, so we're not going to worry about that. Then I'm going to have the map insert power 2 to the val, comma val. So in this case, 2 to the 1 is 1. I mean, 2 to the 1 is 2, right? And then we move up the instruction stack. Does that make sense, everybody? Then I get to 2. 2 mod 3 isn't 0. 2 to the 2 is 4. So then I get to the third one. 3 mod 3 is 0. So I would insert 2 to the 3, which is 8. But here I'm also inserting 2 to the 3. Does everybody see that? So what's going to happen is, at this level, that would become 8. And so now I'm treating this as the inserted set of key value pairs. Then I go to 4. 4 is not mod 3, so we're going to have 2 to the 4, which is 16. I go to 5. It's also 5 mod 3 is not 0, so 2 to the 5 is 32. And then I go up here, 2 to the 6. 6 mod 3 is 0. That becomes 64, but it also does this as well. And so here, the values that I inserted, this becomes key, and this becomes the value. So at the instances where the value was modded by 3, we see that it's different. Does everybody see that? It should be 32. So once you have that written, the next thing you want to do is, okay, I finished func 1, now I go to func 2. Now func 2, what I'm doing is I'm iterating through the current pair, and I print out first and then second. So we see that it sorts by the key, and then we print out the value. And what would happen is it's going to print out in the opposite order. So it'll be 2, 1, 4, 2, 8, 8, 16, 4, 32, 5, 64, and 64, which is choice D. Before I continue, does anybody have any questions about anything I did there? So you're going to have a problem that's going to be similar. You'll have one problem that's either going to be set or multi-set, and you'll have one that's map. So this is an example of a map type problem. So when you get this, put in D, we see that we get that. So now what I want to do is we're going to run make problem 2, and this time we're going to go through a similar type process, except I want you all to work me through it as though you are practicing for the exam, because this is exactly what we want to do. So in this problem, it's going to be very similar. I have in main, so first let me read the problem statement. Given the code segment, select the corresponding output. First thing, what's the very first thing you should do? What's the very first thing? Yes. Outstanding. Before you do anything else, go to main. So in main, what do we see here? What's the type of data structure that's there? Yes. Standard set. So I see standard set. What's the first thing that should go through your mind on an exam? Yes. Yep, we have some sort of type of sorting, and it's a red-black tree. So right off the bat, and unfortunately that doesn't really help that much because all the answers I have here are sort it. So before you even do anything else, just put yourself in the mind of the professor. You have to evaluate whether or not the students really understand how the data structure works. So look at the choices. And what do you think I'm trying to evaluate the difference in your understanding in those, particular compare A and B, in particular compare C and D? What do you think's the difference? In the back, yes. You just had your elbow up. You're scratching your back. All right, yes. Yep, I'm trying to differentiate, and that's what you're going to say too, right? Yeah, we're differentiating the difference between set and multi-set. So if that means you're actually practicing two problems because you can see what the answer to this would be if you replace set with multi-set. So I have a set, I start out with func. So now let's evaluate that. So I'm passing 5. Here. And so now what am I doing? What's going on in this code? Who wants to tell me what's going on in this particular function? I see several people are typing in the Slack. Okay, we are recursively creating values for the tree. That is absolutely right. So what's going to happen is we are going to insert the value and then recurse. So we're going to see that I'm going to have 5, then I'm going to recurse, then 4, then I recurse, then 3, then 2, and then 1. And so when I have 1, when value is equal to 1, I can still call 0, but I'm not going inside this. Does that make sense? So these are the values that I've inserted, and then I have this value 0 that I haven't. And so the next is insert the value, and then to the value, and then recurse. So we're going to recurse, and then we're going to conduct this last part of the line. So now what's going to happen is I'm going to put 2 to the value into the tree. And so 2 to the 0, what is this going to be? A lot of fingers up, 1. So what at this stage, when I insert 1 into this data structure, if I were to print out the results, what would it be? Would I have 1, 1, 2, 3, 4, 5, or would I have 1, 2, 3, 4, 5? First or second choice? Okay, everybody's putting up second. Very good. And the reason why is because when there's a set, there is no duplicates. If this was a multi-set, there would be duplicates. And so now what's going to happen is we're going to move up. So in this case, now we're putting in 2. So 2 to the second is 4. We don't put in 4 because we already have a duplicate. When we move up here, 2 to the 3 is 8. So we're going to put in 8. 2 to the 4 is 16. 2 to the 5 is 32. So we're moving up the recursive ordering. And if we look at the choices, we'll see that I have, for choice B, 1, 1, 2, 3, 4, 4, 5, 8, 16, and 32. And we see that we try to put in 1 as a duplicate and 4 as a duplicate. So the final choice will be 1, 2, 3, 4, 5, 8, 16, and 32. And that is choice A, if I remember correctly. Looks like it is. So you can get full credit for putting A in like so. All right, does anybody have any other questions about that? Okay, why did the order switch? The order switched on the previous problem. It was just that was the way that I was putting them in with the key and the value. But when it's sorted by the key, it gave us the correct results. Okay, done problem 1, we've done problem 2. All right, so what I want to do for the last 20 minutes of lecture is introduce another data structure. We're going to have 2 major ones that I'm left this semester. And this is another one that you're going to revisit a lot when you go into the algorithms course. So the last two data structures, well, the last three, counting trees, are going to have a lot to do with helping you out in job interviews and when you get into more advanced topics. So far, when you've developed priority queues, the first one that we developed was a sorted doubly linked list, and we found the pros and cons. We were able to insert at the beginning or the end in big O of 1 time because we have the head and tail pointers. Sorting required big O of n time for each insert, which had a worst case scenario of big O of n squared for all the elements. For a max or min heap, we had log n insertion, and that helped us be able to get the top element be the minimum or maximum value, depending on whether we were using a max heap or a min heap. The drawback is that there was no intuitive way to be able to get any other values or to have it in any kind of sorted order. We just knew that the values below had to meet some sort of heap property. So the question is, how can we actually start making this a little faster? How can we beat max heaps or min heaps while taking advantage of some of the aspects of red-black trees? And so this data structure we're going to call a binomial queue. And I'm going to walk through the process of how we might do this if this were a heap for a specific data operation called meld, where I have two priority queues, and my goal is to create a new priority queue using those previous two priorities. So let me walk through, and this is also going to help serve as a review. Oh, you all did max heaps and min heaps on the midterm. You won't do this on the final. But if I was melding priority Q1 and priority Q2, first I would check to see which one was bigger. And so on the left-hand side, we see the new value. And in this animation, we will heapify both of these queues. And we see that 18 is bigger than 14, so we put in 18, and then 17 heaps up. 17 is bigger, so that's going to be the next one. 16 is bigger than 14. 15 is bigger than 14. 14 is bigger than 12. 12 is bigger than 11. 11 is bigger than 5. 9, 8, 7. Now 5's the biggest, 4, and then 3. Right. So we see that we picked the largest one and we meld them together. So that means we don't have to be doing heapification because we know, well, we don't have a full-on heapification because what's going to happen is it's inserted in the order that ensures that that the properties are maintained. And in fact, this case, it's sorted. So what I want to do is take some of the old and some new and put it into a new type of thinking about how to structure data. So up to this point, what we've been doing is we've been sorting based on our knowledge of the data element itself. But now what I want to do is I want you to kind of take the binary nature of computers and see how it is we can use this to store specific elements. So take this binary addition. In a typical binary addition, we'd start out here, we'd have 0 plus 1 is 1, and then we'd take in this carry bit. Then I have 0 plus 1, that gives me 0 with a remainder of 1. This gives me 1 with a carry, like so. Rather straightforward. So it's in binary, and our solution would look like that. Now here's the interesting thing. What if I started thinking about them in terms of the powers? So before, so here I have 2 to the 0. These are both 2 to the 1. These represent 2 to the 2. We have 2 to the 3 and 2 to the 4. So now I have 2 of these, 2 of these, and 2 of these. So I have 16, I have 8, I have 2 to the 4, so that's another 8. I have 2 to the 1, so that's another 4, 2 to the 0, which is 1. in all of these, they represent some sort of power of 2. So the question is, can we break down the problem of storing elements by using this property? So if I translate this, we see that initially the sum is 1 plus 2 plus 2, which gives us 1 plus 4. Does everybody see that? Same thing, we have 4 plus 4 plus 8 plus 16 gives us 32. So what this allows me to do is kind of break down these values into powers of 2 chunks. So the question is, how can we translate that into structuring data? So let's take some elements that we would want to put into a priority queue. And here I have them broken up into powers of 2. So if I want to insert it, let's say I take in these values. I have 53, 58, 26, and 31. And I want to cluster those. Everybody see that? Now, this is another power of 2. That's 8. And now I can cluster these as well. Here's the interesting thing. I've now broken the problem into subproblems. So what's the smallest value in each of these? I got 26 and 23. If there was a way in which I could break these down, I could actually know what the smallest value is in each subproblem, which would then allow me to be able to determine what the smallest value is in the entire data structure. So what we're going to do is, how can we actually structure this data? Why are you clustering 26 and 31? This because they were over here. We'll go into a lot more detail as to why that is in a moment. So what properties must our packets have? We've discussed that they're going to be sizes and powers of 2. We have to be able to efficiently, and you'll see what I mean by this term, fuse them together in a moment. And that's going to get back to the question that was asked on the Slack. And as long as the packets provide big O of 1 access to the minimum, we can execute find min in log of n time. So for example, in this specific case, 26, 53, and 41 are the 3 potential smallest values. And so how can we actually do this? If I do this again, we see that I have a power of 8 here. I would compare 18, 41, 53, and 26, and then 18 would be the smallest value. So our analogy with the minimum kind of breaks down when we try to remove the minimum element. So after we lose an element, if we had an element that was in a packet that was in the power of 2, we now lose that. However, we can break those subproblems into powers of 2 as well. So let's say, let me go back to the previous slide, and let's say I deleted 41 from this particular packet. I now have 64, 97, and 93. So before that was 4, and if I subtract 1, that becomes 3. But now here's the interesting thing. 3 is 2 to the 1 plus 2 to the 0, right? So this is 2 plus 1, which means I can cluster them in a different way. I haven't gotten to how I'm going to combine the values again. We'll get there in a moment. So we will go into that in a lot more detail in a bit. So if I remove that, so you see over here, I've removed 18. Now I can break these into 2 to the 2, 2 to the 0, 2 to the 1. So these are all powers of 2. So you would break them like so. And so this mathematical proof kind of just goes over what I have done. So if I have power of 2 and I remove 1, it's actually going to be a summation. So in this case, there was 8 minus 1. So that becomes 2 to the 3 minus 1. And this goes 2 to the 0 plus 2 to the 1 plus 2 to the 2, which is 4 plus 2 plus 1, which is equal to 7. So basically all this says is if you remove one from a power of 2, you can sum up the rest with powers of 2. And this becomes an important property. So now the question is, what do we do with all this, and how do we actually get these pieces together? So now, how can I fuse other elements? Well, first, we're going to sort by the boxes by size. So before I had this, now I sort them by size, and then I sort them by the smallest value in the buckets. So before, I have 26 and 45 are my 2 to the 0. So I would put 26 and 45 here. Then I have my 2 to the 1s. And that gets sorted by the smallest value here. So 27, 28. And here we have 53 and 58. Does that make sense so far? Then I want to take these other two and sort them here. So now I've got 23, 64, 62, and 59. And then I have another one here, which becomes 41, 93, 97, and 64. So it breaks down like this. And so that's why the next slide looks like that. Now we sort the boxes by size, and now we can start combining them. And so here we have 2 to the 0s. It's going to be 2 to the 1. So that becomes 2. And then we sort them by which one's smaller. Then we would move over, and these two, is 2 to the 1 times 2, which is going to be 4. So now we can combine these together. Then we have 2 more of these. We have 2 to the 2 boxes, and that can become a 2 to the 3 box. So the question is, how does that all get there in the first place? So the key thing to remember, and how we can tie the math into data structure, is that there has to be some sort of representation of these values. So here I have 8 elements. But we see that 2 to the 3 is 2 to the 0 plus 2 to the 0 plus 2 to the 1 plus 2 to the 2. And that's the way that every power of 2 works. So that's why when we get rid of one of these, we know that 2 to the 3 minus 1 is going to be equal to 2 to the 0 plus 2 to the 1 plus 2 to the 2. So because we have this, we can actually come up with a sorted ordering. And we look over here, we actually see that this is 2 to the 3, 2 to the 0, 2 to the 1, and look at 2 to the 2. 2 to the 2 is 2 to the 0, 2 to the 1 plus 1. Does everybody see that? So the question is, how do we actually put these together? And so that's what I'm going to spend the rest of the 5 minutes of today's lecture and the first part of Thursday's lecture doing. So we're going to formally define a binomial heap as an order of k, and it will have 2 to the k nodes. And so the way this is going to work is that we are going to use this idea of packets to put the pieces together. We're going to use this knowledge that we've just proven that k groups can add in 2 to the 0 up to 2 to the k minus 1. And then we're going to recursively build binomial trees from those groups. And then we're going to make those new trees the children of that root. And so what do I mean by that? That's what I'm going to spend the last little bit of today's lecture doing. So they are called binomial trees because we rely so heavily on the power of 2. And in algorithms, you'll study one that's even more advanced called a Fibonacci heap, which uses the Fibonacci sequence to be able to break these down. So that's even more efficient than this power of 2 that we're going to be using. And so basically this slide, I'm just going to say that it meets all of our requirements and we have sub packets like so. So let's say I wanted to delete this other element. Let's say I wanted to recall a remove min. So I remove 23, and what's going to happen is it's now going to go to this subtree. And so now these will be our top elements, and I now see that the smallest element is 59. Okay, so meld, I've talked about that, but me, don't need to go over that. All right, so what I would like to do is I'm going to go over these two examples, and then I'm going to conclude lecture. And then what we're going to do is we're going to do problems 3 and 4 to start lecture on Thursday. And then we are going to go over a type of advanced hashing known as cuckoo hashing. And cuckoo hashing allows us to be able to fill up to 90% of the hash without having to rehash. So let's walk through this example. So I want to insert 1 through 9 into the hash. This is going to address the questions that are being, I'm not the hash, I apologize, a binomial heap. So when I insert 1, it's just there by itself. When I insert 2, I'm going to initially have, here's the way it's going to work. When I have 1 and then 2, we're going to see that I can combine this into one packet, and I know that 1 is greater than 2. So it's going to be 1 and then 2. Does everybody see that so far? The next thing that's going to happen when I'm going to insert 3. I'm going to put 3 there, and then I'm going to insert 4. So initially 4 will be here, then 2 to the zeros, and it's going to become 3 and 4. And then what's going to happen is I can combine these. And here's how this breaks it down. So this is going to address the two questions in the Slack. I want to be able to represent this binomially. Everything should have powers of 2. So in this case, I know that 1 is less than 3. So 1 is going to become the parent. And its first, it's going to look like this. So this tree will now become a subchild of that tree. Does that make sense? So let me walk through the animation in the slides. So we're going to see that 3 is going to be there. Then 4. 4 is going to become a subtree of 3. So that's 2 to the 1. And then we combine them together. And now we have 2 to the 2, of which 2 to the 0 and 2 to the 1 plus 1 are summed up. So now we have our binomial property. When I insert 5, I'm going to insert 6, and it's going to follow the same pattern. Then I would insert 7. Then I'd insert 8. 8 becomes a subtree of 7. 5 is less than 7, so 7 becomes a subtree of 5. So here's what's going to happen next. Now we have 8 elements. So now we have 1 and 5. 1 is the smaller one, so guess what? Its next child is going to become 5. So it's going to look like this. And we see that we have 2 to the 0, 2 to the 1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And so if I were to insert 9, it would look like this. All right, so now I'm going to work through one last example, and then I'm going to dismiss. And we will start on working through our own examples in lecture on Thursday. So I have 1, then I insert 9. 9 is going to become a subtree of 1. Then I'm going to insert 8, and then 2. So now 2 is less than 8, so 8 is going to become a subtree of 2. 2 is less than 1, so now 2 becomes a subtree of 1. So now I'm going to insert 7 and then 6. 7 is going to become a subtree of 6. And then I'm going to insert 5 and then 3. 5 is going to become a subtree of 3. 3 is going to become the parent of 6. So it's going to look like this. It's going to have 3, 5, 6, and 7, like that. That's what's going to come up. Does everybody see that? And then 3 is less than 1. And so now 1 becomes this. And then I insert 4 as the last value. All right, so please let me know, Lydia and Matilda, if that addressed your questions, because both of your questions pertain to that. Does anybody have any other questions before I dismiss? All right, on that note, it is 2 o'clock. Please email your mentors tonight. Let me know if you have any questions, and I will see you all on Thursday. All right, so Natalie, to address that question, I'm going to get more in detail in the code, but basically what is going on here is that they are all in an array. And it'll be sorted by this value. And so 1 would be first, and then I would find 4 over there. So let me know, Natalie, if that addressed your question.